looking at the symmetries and conservation laws. That's what we left off with last time. So the symmetries, first one was that time is homogeneous. And always, as always, we're talking about inertial reference frame, otherwise all bets are off. Inertial frame. Time is homogeneous, and that leads to that means that the Lagrangian is not explicitly a function of time. That leads to BL EQI dot equals a constant. But this L is outside of the summation. And for the general form, with the quadratic form here, IJ dot QJ dot minus U. For that form, then T plus U equals constant. So that's the thing we ended up with. That was our last calculation. And these next conservation laws, oh, and I should also say, we started this with defining the cyclic coordinate. You guys remember what the cyclic coordinate was? The cyclic coordinate was the coordinate that was not there. So if a Lagrangian is missing a certain coordinate, it has a generalized velocity, then you immediately get those conservation laws. Remember? Linear momentum, angular momentum. So that's what started this whole thing off. Now the next symmetry that we're going to talk about, so this is one. The second one is that space is homogeneous. It basically means that any point in space is as good as another point in space. We had seen that projectile motion xy point. Any point is essentially as good as any other. So because of that, we're going to turn the argument around now. We're not going to have a cyclic coordinate, but we're going to impose something on the Lagrangian. We're going to say L is unchanged by an infinitesimal translation. Infinitesimal translation. And that translation means the entire system is being moved by a vector epsilon. So that's our infinitesimal translation, epsilon. And demanding that L be unchanged by this means the following. I'm going to imagine that the translated, since this is an infinitesimal translation, I'll do this. Sum of EL, I'll do this one. So L sub epsilon is L plus DL. And what that is going to be is L plus, think of Taylor expansions, DL, dr, dotted dr, plus sum over DL, r dot, r dot. And for it to be unchanged, we're going to require that this vanish. Kind of a first derivative type of criteria. Right? We require that that vanish, but we've got an infinitesimal translation of the entire system, epsilon. So what we have is dr is equal to epsilon, but dr dot is equal to 0. Because epsilon is just a constant. So we're requiring that this change, that the Lagrangian be unchanged. So it's unchanged up to the first derivative. And therefore, we have sum over dl r dot epsilon equals 0. And let's go ahead and put a little subscript on these. This is I. We're doing a summation over those. But the point was is that the whole thing is translated by epsilon. So the epsilon doesn't carry a subscript. So because of that, we've got epsilon dotted into the sum dl dr sub I is equal to 0. So now we do an argument similar to the fundamental lemma in the variational calculus. Namely, this thing is arbitrary in direction. Therefore, when it's multiplying, it has to be 0. Let me come over here to the left. So, continuing the argument, epsilon arbitrary, so sum of dl r sub I equals 0. But we have the Euler-Lagrange equations, and the Euler-Lagrange equations tell us that the dl dri is the time derivative of dl dr dot. So that equals 0. Okay, this keeps getting better. Now I can pull the complete time derivative outside of the sum. L R I dot equals 0. You guys know complete time derivative of something vanishing means the thing here is a constant. So this is our conservation law. What do you think we're looking at? Now remember what dl dri dot was. Cartesian coordinates. We're doing Cartesian coordinates right here. Yep, linear momentum. So this is the sum of all the individual linear momenta. So for the system, the sum of the linear momenta vanishes. So this means the sum of the piece of I equals, I'll just write capital P, total linear momentum is conserved. So this is what we have. In the homogeneity of space, we're required that the Lagrangian be unchanged, and we obtain conservation of linear momentum in the entire system. It's on here first. You're going to see these kinds of arguments later on in theoretical classes. Quantum mechanics will use this argument to derive the form of the operators, things like that. Infinitesimal translation leads to conservation of linear momentum. So yeah, make sure we put this down here in bold letters, conservation of linear momentum. Yeah, the Lagrangian system is pretty impressive. That was, here's your takeaway for linear momentum. So we're going to do the same thing. It's a little trickier with angular momentum. So now we have energy, linear momentum. The symmetry that leads to conservation of angular momentum is that space is isotropic, which means one direction is as good as the next. So if I point my device in this direction and I point it in that direction, it shouldn't make any difference, provided I'm not on a turntable. Provided, I'm in the correct reference frame. So yeah, I'm going to erase this. But yeah, you see how the argument goes. We demanded that the Lagrangian remain unchanged, so this part had advantage. And we're going to do the same thing for the next isosceles space. Keep numbering these spaces isotropic. Inertial reference frame required. Rotation of the entire coordinate system must leave the Lagrangian unchanged. So then, infinitesimal rotation. This is getting a little ahead of the game in that we're going to do rotations in rigid body mechanics later this semester. Okay. A little ahead of that. Infinitesimal rotation leaves L unchanged. So this infinitesimal rotation looks like this. We have a vector d phi, and we apply a cross product to say r sub I right here. And the cross product, so we're going to get a dr sub I equals d phi cross r sub I. Think of that as a cross product, and let's see if I can get my pictures of this somewhat. See, if I do a cross product, it's an infinitesimal rotation with this r sub I. This one is into the board, so to speak. Cross product into the board. I'll put a little circle around like that. And the d phi infinitesimal rotation of the entire coordinate system, whereas this is just an individual here. So dr sub I dot is just d phi to a velocity. So that's what the infinitesimal rotation does to any vector. And what we do now is the same as before. Now we're going to do L sub phi. We will let L plus dl. And this dl has the form as before, dl dr sub I dot dr sub I plus dl substitution. So we have sum over L plus I dotted into B cross R sub I. And we've got the sum over L R sub I dot. And again, BP cross R sub I dot. And now we make use of A dot B cross C. The cyclic nature of this expression, we have C dot A cross B, and the one we want is B dot C cross A. So now we'll have sum over B L. Actually, let me make use of this. So the one that comes out front is the DP. So we have sum over DP dot R sub I cross BL R sub I plus sum over DP dot R sub I dot plus BL R sub I dot. And this, first of all, the D feed is not carrying a subscript, it's the whole thing, so we can pull it out. We're gonna make that same assumption. So what we have here is R sub I cross, I'm using the Euler boundary equation, E over P, PL, R sub I dot. So Euler boundary equation right here, put this inside one sum plus R sub I dot cross L sub I dot. Okay, once we write that down, who sees the punchline? This is the product rule, because I've got this cross the time derivative plus the time derivative cross the non-time derivative. And this here is P sub I. This is P sub I dot. So I have R sub I cross P sub I dot plus R sub I dot cross P sub I. So that's a complete time derivative product rule. So what I have is, it's going to be the same argument before, because, wait, I missed one. Because this is arbitrary, I'm going to say this sum here vanishes, and then I'm going to say this sum is the complete time derivative of something. Okay? So I'll do that in I'll do that in one step. So I'm just going to point here, arbitrary. And then I'm going to write here, I have D over dt, that can be pulled out with R sub I cross P sub I equals 0. And that, of course, is the total angular momentum. So the total angular momentum is conserved. So since that's the total angular momentum, we have the conservation of angular momentum. Okay. Leave a little space in your notes. You fill in any gaps there. Right, that the argument is there. There's the conserved quantity, and that's for the entire system of interacting particles, conservation negative. There you have it. Yeah, that's a really important chapter, the relation between symmetries and conservation laws. And before that, the relation between symmetries and cyclic coordinates. We saw with cyclic coordinates, these conservation laws just fall right into our lap. So we should construct a couple more of these now, cyclic coordinate problems, just to see how that works. This one we demanded it, so we said these are symmetries of space and time, and therefore the Lagrangian system of mechanics has to have this form, and they're delivered. Okay, so we'll do some more examples here. We don't have anything for next week, right? So we're going to start a list of things for next week. I'll kind of work along with us. So let's do this. Homework problem. I'll do the first one, but these are all for this symmetry type of problems. Suppose we have X, Y, Z, and we happen to have an infinitely long mass. The line mass distribution is infinitely long. Infinite long mass. You guys have done this in electricity and magnetism, conceivably, right? When you're doing Gauss's law, that kind of thing. So what coordinate system would you choose? Cylindrical, right? So immediately we say L equal to L of rho, phi, and Z, rho dot, phi dot, Z dot. What are the cyclic coordinates in this problem? Why?
Because the line of mass is just always there wherever you are on the z-axis.
Exactly. No matter where you are in Z, it's infinite in that direction, infinite in the other direction. So yeah, this is cyclic. What else?
The angle.
The angle.
Yeah.
Same argument, wherever you are. Angle-wise, you're just looking at this infinite line. What about rho, which is the distance from that line?
Well, the line is infinite.
There's an argument for why rho is not cyclic. And that is, we don't know about the strength of the charge, right? And if this charge is stronger or weaker as we go closer or farther away, we notice that. So it's not going to be, so rho is not going to be cyclic. But since these two are cyclic, what are the two conserved quantities? Exactly, and just automatically based on this. So because these are cyclic, we know that dl d phi dot equals constant, and dl d z dot equals constant. And so this one is, I could call it p sub phi, this one I could call it p sub z. So good. I said homework, but this one's actually, and of course energy. Energy is conserved and we don't have the time there. So this constant, that's constant, and energy. So let's do another one of these. You guys can write this one up anyway for the homework, it's good for your records. So the next one, we can discuss it, you guys can write it down. Okay, so this next one here is, again, we're in X, Y, and Z. But this time there is cosmic dumbbell mass distribution. So now L equals L of what coordinates? And the second question is find the conserved quantities. Another good one. A little different. Play around with these. So again, we've got X, Y, Z. And we'll extend this line here. And we'll say the entire, so we'll just say, we're always in the field of something, right? It's field of X positive Y plane. So what we have is the XY plane, except only for positive Y, so that would be this half, okay? So based on that, what's the form of Lagrangian? You're definitely using Cartesian coordinates now. So I'll just write find the form of L of X, Y, Z, X dot, Y dot, Z dot, and conserved quantities. And this last one I'm going to put up here, right? This one we just did. The second one you guys will see right away. This one you'll see in a bit. The last one is interesting. Suppose we had a helical mass distribution going up the z-axis. Cosmic helix. Okay, we're approaching these things in our space capsule. I'm going to go ahead and erase this one. Infinite helix. This last one requires us to channel the proofs that we just did. Okay? Because homework, infinite helix. And this one will really drive the point home. It's kind of fun. So suppose we have for X, Y, Z, and along the z-axis, we've got this helix. So the helix is like this. R of the helix. It's a constant. First of all, we'll use cylindrical coordinates. The helix itself is defined by A, and then, so already A equals constant. So it's just a constant. And then the angle, and then the Z is equal to H over 2 pi times phi. So what that means is every time you go around 2 pi, you go along this edge. So that's the parameterization of the helix. So now L, we've got rho, phi, Z, dot B dot C dot. And the symmetry here is if you've got that helix, if you were to go, if you're at some fixed distance from it and you go around and up, you go the proper distance around and up, then it'll always look the same to you, right? So that's the symmetry here. And because of that, we're gonna do this. L equal, that was called L naught plus DL in such a way that DL is equal to 0. DL equals 0 for the transformation that leaves the helix looking unchanged. And as I said, we're going around, we'd be coming around here counterclockwise and going up in such a way that it never changes this look to us. Or the transformation that leaves just for the transformation, right? The transformation is going up and around. That's a neat one, so I'm going to leave that one for you guys to ponder. We've got a couple easy ones, we've got that one. And like I said, so in fact, let's talk about what is this step going to be? It's going to be those differentials that we did. Okay. Making use of these facts, so it'll be a fun one. Okay, that's our symmetries and conservation laws discussion. So where do we go from here? We have to set up a couple more Lagrangians just to be able to work on. So far we just have the mass and the spring, right? Mass and the spring. I think we'll head off into small oscillations. Theory of small oscillations next. Yeah, small oscillations with many degrees of freedom, that's a subject where the Lagrangian method is really nice and systematic. So that's a major chapter in the semester. I think we've missed that. I don't think so. I want to build some. So next topic, small oscillations. Once again, so we spent a lot of time on that last semester. But this time, we have anything from 1 degree of freedom to many degrees of freedom. So actually, I'll start with 1 degree of freedom. There's a little bit more here to be had. How much of the cycloid did we do last semester? Fair amount of the cycloid, right? So let's, we may even have done it small oscillation, but it'll be a good one to start with. So the cycloid, and in fact, this is going to be the inverted cycloid. So the inverted cycloid, we've got x-axis, a y-axis. If you guys remember how we rolled that thing out, this would be minus 2r, this would be 2 pi r, right? And since we've derived this before, I'll just write this, x equals r theta minus r sine of theta, and y equals r cos theta minus r. So we've seen this before. How about its Lagrangian? Now suppose we have a track, there's G, and we're gonna let something slide down here. Have we had that before? It's Lagrangian? We just learned about Lagrangians. We may have done the energy last semester for this. Sometimes I like to do that. But we want to get the Lagrangian. So for this object, and the Lagrangian, first of all, we just have to do T equals 1/2 m x dot squared plus y dot squared, and u is going to be mgy. But this won't do because we have two coordinates and there's only going to be 1 degree of freedom. So what we do is, I'll fill this in right here. Actually, I've got room right here. So the x dot is equal to r theta dot minus r cos theta dot. And the y dot is minus r sin theta dot. Okay, so yeah, we have to get this thing here, and 1/2 m x dot squared plus y dot squared 1/2 m, and then we have r squared theta dot squared minus 2 r squared cos theta dot squared plus r squared. Oh, this is the cosine squared. Plus r squared cosine squared theta. Theta dot squared plus r squared sine squared theta, theta dot squared. So these two are going to simplify. So we're going to end up with the following: 1/2 m, and then we're going to have 2 r squared 1 minus cos theta dot squared. Now you're going to notice I'm not going to cancel the twos in there, because what we're looking for is a standard form. The standard form of the Lagrangian is this. We're going to have a 1/2, we're going to have a 2m r squared 1 minus cos theta, and we're going to have theta dot squared. And then I'll subtract off the y, which is r cos theta minus r, m g r cos theta minus r. I'll put a box around here as well. So this is t minus u, right? And so it's t minus u, but what you'll notice is we've got this generic form, 1/2 on the right, a of theta dot squared minus u of theta. See, so that's the generic form. It's a bit more general than 1/2 m x dot squared, right? It's got the same form, but this itself is a function of theta. And we've actually seen that before. Remember those general Lagrangians with n dimension, n variables, a, I, j, and q, right? So there's another example of the a of q. find the frequency of small oscillations. This is a classic thought. Find the frequency of small oscillations. Where's the equilibrium on this system? Picture tells the story, right? Well, what angle is that equilibrium associated with? Pi. Right? It goes from 0 to 2 pi, about theta equals pi. Formally, of course, you can, I mean, it's all in the picture. You can show that you got a local min at theta equals pi and so forth. So, filled up my board. I'm going to go ahead and erase this. So yeah, and when you write this one up, definitely take it to the top because it's all useful development, and then you quickly knock out the last thing. But let me, I've got 5 minutes. Let me talk about this thing here in the general terms. So this is the general Lagrangian of small oscillations for 1 degree of freedom. We didn't have quite that generality last semester when we just had a constant here. But this plays a big role. So for L equals a half A of Q, Q dot squared minus U of Q, what we do first is expand U of Q about its local min, right? About its local minimum. Local minimum at Q0. Okay. So yeah, we've got U of Q equals U of Q0. Same as last semester, U of Q0, Q minus Q0, 1/2 U double prime, Q minus Q0 squared. And we're going to argue this is an arbitrary constant, doesn't bother us at all. I got one more thing about the Lagrangian system. Okay, this one, of course, is 0. And so we essentially have, so let x equal q minus q0, then we have u equals 1/2 k x squared, and we're going to let k equal u double prime, put them on u double prime of q0. Right, so that takes care of part of this. But what we have new is we expand A of theta, or A of Q. A of Q equals A of Q0 plus A prime of Q0 minus Q0. Right? So you just got to be comfortable with these expansions, and of course we are at this point. And the thing about A of Q is that we're going to keep Q minus Q0 small enough, so small that this term here is negligible compared to that one. Okay? So this magnitude A prime of Q0, Q minus Q0 is much less than A of Q0. And then guess what we're going to name A of Q0? We're going to name it M. Why not use the old letters, okay? Because having done that, having done these 3 steps here, we get what we're going to call the small oscillations Lagrangian. It now looks just like our simplest case. This is T minus U. In fact, once we look at this, we know the answer. We know what's going on. frequency of small oscillations for this guy. Or can it only be K over M? Exactly, right? So once you have something of this form, you actually already know the answer. We've essentially done all the work. Well, Euler-Lagrange equations give Newton's law for this, right? So immediately you know that your omega squared is K over M. But what you're going to see is even for this problem, this recipe is very important. Because now our A of theta is this thing. And the key here is you're evaluating that, and you're saving yourself an enormous amount of work. You're evaluating this thing at its equilibrium. Right? So, and you'll get an interesting result on this one. That's a good place to stop. So, we're good. Do this one really thoroughly. Good. She left this bowling ball around.